Hello and welcome to this last video of this semester. In this video, I'm going to solve with Python some exercise questions B and C from exercise 1 and solve exercise 3. Okay, so in exercise 1, we have a Galton-Watson process with reproduction law 3/8, 1/4, 1/4, 1/8. We already found the exact value of the probability of extinction. It was -3 plus radical 21/2, and which was about 79%. Now, question B, draw with Python the graph of the probability generating function phi, as well as the first bisector on the interval 0, 1. Okay, and then solve numerically the equation s equal phi of s and compare with the results of A. Okay, so as usual, we import matplotlib and numpy, and we define our function phi. So we know that phi of s is 3/8 plus 1/4s plus 1/4s squared plus 1/8 s cubed. Okay. And if we want to draw, we draw from 0 to 1. So we divide the interval 0. We can go from 0 to 1.05. It's not a big deal. And yeah, we can go. So we can put from 1. Not a big deal. And so we plot the graph of phi. So we plot t versus, or phi versus t, phi of t versus t. And then we plot the first bisector, which is TT, actually, first bisector. And these two commands are just to plot the vertical and horizontal axis. So shift enter. And here is our graph. So in red, actually, in dashed red, we have the first bisector. And in blue, we have the graph of phi between 0 and 1. So we always have 1. So the graph intersects the first bisector always at 1. But here we have another solution actually here. It's around 0. So about 0.8 actually, but it's not very clear. So this is the graph. So now we want to compute numerically. We have two ways to compute numerically the roots of s equal phi of s, which is a polynomial equation of order 3. So the first way, because Python has, or NumPy more precisely, has a routine for finding the roots of any polynomial. So we introduce the polynomial in this way. So we just introduce the coefficients. Okay, 1, 2, minus 6, 3. 1, 2, minus 6, 3. And the command is np.roots. So there are 3 roots, minus 3.79 and 1 always, and 0.79.12. Okay, so this is the first way of solving numerically the equation s equal phi of s. So this is the probability that we got actually. Okay, this root is rejected, as you know. Now the other way is to use a fixed point iteration. So we start from 0 and we let q1 equal phi of q0 and q2 equal phi of q1 and so on. We know that this sequence converges to the fixed point to the solution we are searching, which is 0.79. So if you want, we can do the first 20 iterations. So here are the results. So we start from 0, then 0.375, 0.5, and so on. So it's increasing actually, as you know from the theory, it's strictly increasing. And after 20 iteration, we are at 0.7793, which is very close. If we want more precision, we can go to a higher accuracy, for example, 50. Okay, after 50 iterations, we are at 0.7910. So the first 3 decimals are correct, actually. Okay, we can go to 100 if you like. So this concludes exercise 1 with Python. Okay. Let us put here 0.05. Okay. Okay, exercise 2 was the same actually. but with different coefficients. And we know that the probability of extinction was about 0.22. So we do the same thing actually. So we can plot the graph, and now the graph is more clear actually. This is what I wanted to illustrate in the lecture. So the graph of phi, in the case where mu is bigger than 1, meets the first bisector into 2 points. One at a smaller solution, which is here actually. So now the graph is the graph is similar to the graph in exercise 1, but because the smallest root in 0, 1 is smaller, the picture is more clear now. Okay. Now we shall see later that if mu is less or equal than 1, then the graph will be above the first bisector. So we'll have just one root instead of 2. Okay, so we see here graphically that the intersection point is about 0.2. And of course, we can repeat the same, we can compute it numerically as we did in chapter 1, in exercise 1. Okay, and now the third exercise, a Galton-Watson process was a Poisson reproduction law, okay, with parameter lambda. So recall that the mean value of xi is lambda, okay? So the first question is to draw the graph of the PGF for different values of lambda, and then to approximate the probability of extinction in each case. Okay, let us start with the first question. So it's very easy actually here to do some algebra and to compute exactly the probability generating function of xi. So it's by definition the expected value of s to the xi, which is actually s to the. So what are the values taken by xi here? For a Poisson random variable takes all integer values, so from 0 to infinity, with probabilities e minus lambda lambda k over k factorial. So this is just pk here. This is the Poisson law. Okay. So now, since I have a constant factor here, e minus lambda, I can put it outside, and then lambda k sk, I can write it as lambda s times to the power k. So there's no sk here, there's an error. Let me correct that. So e minus lambda sk, lambda s, and there's no sk here. Okay, so now we have the sum of lambda s to the k over k factorial, k from 0 to infinity, and we recognize that this is just, and there's an error here, c plus lambda s. Yeah. So this series is just the exponential of lambda s, as you know from calculus. So we get to e minus lambda times e lambda s, and this is just e lambda s minus 1. So this is the PGF, very simple formula for the PGF of xi. Now, if we want to compute the probability of extinction, we have to solve the equation e lambda s minus 1 equal s, or e lambda q minus 1 equal q, but this is not doable analytically, so we have to approximate the roots. Okay, so there's no formula because this is not a polynomial. Even if it was a polynomial, if it was a polynomial of degree 4 or 5, it would be very difficult to compute analytically the roots. Okay, so what we do is we approximate the roots by using either the fixed point iteration or another numerical method. Okay. Now, first thing to do is we want to draw the graph of phi for different values of lambda. Okay, so let us start with first with lambda equals 0.5. So we just we introduce a function of two variables now, lambda and s, because we can change lambda. So this is just, we call it phi. So we overwrite actually the previous phi. You can call it anything you like. And then we plot phi of lambda t for this value of lambda against t, and we plot the first bisector as usual. And these two lines are just for the coordinate axis. So shift enter, and we get precisely this situation here. And here actually, this illustrates the case where the probability, the mean value of the reproduction law is less than 1. It's 0.5 in this case. Okay, so so the tangent actually at 1 is 0.5. It's so the graph is above the first bisector, and therefore there's only one root. So the probability of extinction is 1 in this case. Okay. So almost surely the population will die. Why? Because the mean value of offspring is less than 1. So individuals do not reproduce enough in order to maintain the dynasty. Okay, so this is the case where mu is less than 1, and mu equal 1, same thing actually. So now we have the first bisector is now tangent, okay, to the graph, and here q as well is 1, we know, and we can compute it numerically. We don't need, because you know. Now for lambda equal 2, we get, as in exercise 1, we have two roots now, 1 and something smaller, and we choose the smaller one. Okay, and for lambda equal 3, the probability of extinction is even lower. Okay, so it's about 0.05%. Okay, why? Because the mean value of reproduction is high. So, right, or if you like, the probability of leaving no offspring is small, because the probability of leaving no offspring is e to the minus 3 in this case. It was e to the minus 2 in this case, right? So now this is why we get a smaller probability of extinction. Okay, and now we can solve numerically the probability of extinction in the case lambda equals 0.5. We know actually that the exact is 1, but we can do it numerically. So this is in the case lambda equal 0.5. So we don't need to print everything, but after 100 iteration, we get 1, right? So I just do 100 iterations to have a more. If you want to do a smaller, you get, for example, if you do 20 steps, you get 0.99. Okay, but 100 is a better choice. For the case lambda equal 1, we know that we have 1, and after one iteration, actually, you are almost there. Okay, if you want a bigger value, you can go to 200, and it's pretty close actually. But we know that the theoretical value is 1. Okay, let us go to 500 if you like. So you see that we have a better approximation. Yeah, let us take. Okay, anyway, so you can play as much as you can, as you like. And now for lambda equal 2, so I'll go to 100. So the probability is now about 20%, 20.3%. Let us do a better approximation. Yeah, so it doesn't improve very much. So it's about 20.31% in the case lambda equal 2. Okay, and in the case lambda equal 3, it's about 0. So yeah, it's about 5.95%. Doesn't improve much after so many iterations. Okay. So what is the interpretation? So when lambda gets bigger, the mean value of reproduction gets bigger, and so the probability of extinction gets smaller. Or we can say that when lambda gets bigger, the probability of leaving no offsprings, which is p0, is e to the minus lambda. So it's smaller, gets smaller and smaller. So it means that the individuals are more likely to reproduce, and therefore keeping alive the dynasty. Okay, so this concludes this short video about implementation in Python of exercise 1 and 3. And this also concludes the course. So in the exam, as I told you, the exam will include chapters 0, 1, and 2 only. If you are really interested, actually, I encourage you to read chapter 3 and 4, which are very small. Actually, you can read them, and they are important, actually. But now, since we don't have enough time, and because you may also be tired as well, so I think it's better to just stop here. And as you know, I told you actually that I may ask you a small question or one exercise about chapter 0 on 15 points. So because now we just have 3 chapters, so I must ask you from chapter 0 actually, and which took us some time. So, but don't worry, it will be a simple question. So, and I may ask you to write a small piece of code in Python. So don't worry, it would not be more difficult than this. Okay, just simple syntax. Okay, so thank you for your attention. I hope you learned something useful, and see you soon.